Last time we started on section 3.2. We're talking about addition of whole numbers. And we're on the second page where we're going to look at a definition of the phrase less than. So if we have whole numbers A and B, and A is less than B, that is written with that less than symbol, A less than B. This is true if and only if there exists a natural number. Remember, natural numbers are like the counting numbers, 1, 2, 3, so on. K, such that A plus K is equal to B. So what it's saying is that if I can add a little bit to a little bit to A, add some number to A, and I equal it, and it is equal to B, then the A was less than B to start with. Right? If you can add a little bit to it and it's equal, then it was less than to start with. So we're going to give the similar description for what it means to be less than, but use subtraction instead of addition. So most of what we're going to write down is going to mimic the phrasing of exactly what's here. Like we're going to write down for any whole numbers A and B. All that's going to be the same. The only part that's going to be the same, that's going to be different, is this ending part where we used addition. And instead, this one's telling us it wants us to use subtraction. Okay? So go ahead and write down all those pieces, but your statement at the end needs to include a subtraction statement about A, K, and B instead of an addition statement. Some of you are staring at me. All I'm telling you to do right now is just to start writing the same thing. It says copy-paste without the computer. Yeah, that's what it says. Write the definition of less than. I've already got a pretty good definition going for me. I'm going to copy what I have so far. So up to this point, I've just copied. I have for any whole numbers A and B, A is less than B, written A less than B, if and only if there exists a natural number K such that. Okay, that's exactly what I said before. But I need a subtraction statement in the end of this description instead of an addition statement, still using A, B, and K. So what would that subtraction statement have to look like? Right. So B minus K equals A. Or if you prefer, you can write A equals B minus K. Same thing. Right? So adding the value to A to equal B is the same as subtracting the value K from B to equal the value of A. And that's what the statement says. In your homework, you're going to have a similar question, homework or group work, I can't remember, that asks you to do the same sort of thing, but with the statement greater than. Okay, it's going to be very similar. Your structure of your language is going to be very similar. You're going to create a statement in the end that's going to use either addition or subtraction. If it tells you which one to use that, of course, but if it doesn't, you pick. But you make the statement about things being greater than, right? So if A is greater than B, what would have to be true? Well, I'd have to be either able to add something to B, or I'd have to be able to subtract something from A. Right? We're just changing this sentence structure around in terms of the equation sentence. Okay, you ready for the next set? These are properties. All right, properties of whole numbers. We use these properties all the time, and we seldom think about the fact that we're using them when we do. Our first property is probably the least acknowledged property. It's called the closure property. The closure property says that if you have two of a specific type of number, in this case we're talking about whole numbers, and you add them together, and specifically we're doing addition because we're in the addition section. We'll do the same sort of thing with subtraction and multiplication and division. We'll do a set of properties. So if we're adding the numbers together, we get another whole number. Now think about that. That may seem like an obvious fact, right? Like obviously if I take two whole numbers, I get another whole number. But it's not true about all types of numbers. For example, if you were to take two odd numbers and add them together, will you get another odd number? You won't. You'll actually get an even, right? If you take two numbers that are, that's an example of subtraction or multiplication I can think of. Let's say you take two numbers that are divisible by 5. Okay, so divisible by 5, they're multiples of 5. So we've got 5, 10, 15, 20, things like that. If I add two numbers that are multiples of 5 together, will I get another multiple of 5? I will. So some systems of numbers will work, some groupings of numbers will work, and some simply won't. Whole numbers work. Two whole numbers added together give you another whole number. All right, so the next one that we're going to look at is one that you've seen and used a lot. It's the commutative property. It's the same property that children use all the time when they're first learning their addition facts, right? So oftentimes they learn all their additions like they're plus ones, right? This is the plus 1 week. We learn all of our plus ones. But then when we get to the next week and we're doing our plus twos, we don't have to do 1 plus 2 because we already know 2 plus 1, right? Commutative says that the order of our addition is irrelevant. I can add 3 plus 5 or 5 plus 3 and I get the same thing. So we do this with children all the time. However, it doesn't mean that they always know one direction as well as they know the other direction. One of my children, this is a multiplication example, but it still holds. One of my children's really good at knowing that 6 times 8 is 48, but if you ask her what 8 times 6 is, she blanks. Every time. She has not mastered the idea of the commutative property of those values just yet. She's still working on it, right? So just because it seems obvious to us that this addition is irrelevant of the ordering, it's not always obvious to kids. The next one is the associative property. The associative property talks about the ordering of the additions grouping and whether it matters. So on this one, you notice the A, the B, the C, it's in the same order on the left and the right. I didn't change the order. All I changed was how the values were associated, how they're grouped together. On the left, the A and the B are grouped together. On the right, the B and the C are grouped together. And as you know, parentheses tell us where we start in a problem, right? So we start with the addition of A plus B on the left, but we would start with the addition of B plus C on the right. So it isn't so much about switching things around as it is about choosing what we're going to add together first. And sometimes it is nicer to add certain pieces together first. In particular, we're going to see a method for addition here a little bit that's called making 10. If you can add numbers together that can end up giving you a value that's 10 and then add something else later, that's usually preferable because 10's a really nice and easy 2-digit number to work with, whereas maybe 13's not, right? So this gives us a lot of freedom in being able to just change the ordering of things. And the last one is the identity property. There is this is the additive identity property. Please write that in. That may seem sort of obvious because we are in the additive section, but there will be a multiplicative identity property that we will do in section 3.4. And when we get to that one, the multiplicative identity is not the same identity as the additive identity. Okay, so the additive identity is the number 0, right? That is the additive identity. The property says that that number has the property that when I add it to anything, the anything doesn't change. So if I add 0 to A, the A won't change. If I add 0 to 5, the 5 doesn't change. And again, it seems sort of like, well, these are the easy addition facts that the kids know already. And yet, we do this, and we use this property when we solve equations later on in algebra. Right? This is what happens when you add 3 to a negative 3 and you get 0. You chose to add 3 on purpose to try to move it to the other side of an equation, usually. But the reason is because when I add these numbers together, 3 and negative 3 add to 0. So this is the additive identity property. Okay, so you have 4 examples. What I'd like for you to do is I'd like for you to pick which of those, and there's not necessarily a one-to-one correspondence here, what property is being displayed on A through D. Just write what property you believe it is to be next to the problem. And then turn to somebody nearby and just see that you have the same answers, or if you don't, see if you can reason through which one might be the right one versus which one might be a misconception. Gracious. When you think you have all 4 of them, or a good guess for all 4 of them, share with a neighbor, compare notes. If you have an identity property, you're going to use the word additive with it, additive identity property. In this section, it's not super important, but once we sort of merge these sections all together, it will be important. All right, let's take a look together. What do you believe the first one's property is? Commutative. Does everybody agree with that? Looks like commutative to you? Cool. Yeah, it's commutative. Don't know why I'm using red. Let's try a different color. All right. That's a different color. How about the property for B? Does that look right to you guys? Yeah, and as I was mentioning it, if you don't write additive right now, it's not that it's unclear, but once we have 2 identity properties, it will be. So just get in the habit of writing additive identity for now. How about third one, C? It's commutative. So sometimes we get this idea in our mind that just because there's parentheses, it must be associative, or when we have another property, it must be distributive because there's parentheses. Those are 2 properties that involve parentheses. There are parentheses here, but what actually changed is the ordering of the things that are inside of it, right? Yeah. So even though it looked like it might have been, it's not. It's a commutative property, not associative. How about the last one?
Associative.
Yeah, that one is associative. Okay, so the order of the numbers 5, 3, 2 on the left is the same 5, 3, 2 on the right, but the grouping parentheses are around different quantities. Okay, the next set of our lesson is the part that I've been sort of like drumming up as something you're going to really like. So are you ready for it? We're finally there, huh? You're ready. Awesome. Okay, so all of what we're going to be doing in the rest of this section is talking about strategies that can be used for addition. Okay? Strategies to use for addition. So your mind should be anywhere from pre-K to about grade 2. This is the kinds of things that you would see in those curriculums at different points for different stages, right? Different ones of them for different stages. Our first, we have 3 basic addition strategies. One of them is called the counting on strategy. So if we have an example of something, we'll make something up. Let's do 5 plus 3 so that I can use some numbers. We start with one value, and it doesn't even matter necessarily which value. So let's say we're going to start with the bigger value, 5. And we count up and the additional amount of the other values. So we do 5, and sort of in a real like visual sense, we go 6, 7, 8. There's 3 on my hand, right? And I ended with 8. And kids like to use their hands, don't they? They do. And so we end up with 8, counting on. And you can also talk to kids about the fact that this happens quicker if they start with a bigger number than if they start with a smaller number. But no matter which one they start with, it's still going to work, right? If we start with 3 and we go 4, 5, 6, 7, 8, we still end up with 8. Okay? This next one may not be familiar to you, but I have definitely seen it in curriculum since, at least since my 8th graders were learning addition. Okay, so in the past 7 or so years, I have definitely seen this in curriculums. So this is the idea of doubles. So what you often will see when a curriculum uses this is that the kids don't go through their plus 1s and their plus 2s and their plus 3s in that order. What they first learn is they learn their doubles. They learn 1 plus 1, 2 plus 2, 3 plus 3, 4 plus 4, all the way to 9 plus 9. It's a different strategy, right? So they know those doubles first. And then the next thing they learn are what are called near doubles. Okay? Nobody said you have to like this, by the way. But if you have a curriculum that's teaching it, you need to know what you're talking about, right? Okay. So near doubles means 2 numbers that are almost doubles of each other. So for example, if a child knows that 3 plus 3 is 6, that's one that they know, then they can use near doubles for 3 plus 4 to think about 3 plus 4 as 3 plus 3. I already know that one, and this is just one more. So they say 3 plus 4, and they go, well, 3 plus 3 is 6. So this is one more, so it's 7. Again, it doesn't work for all numbers, right? 3 plus 8 doesn't work right here if I know my near doubles, right? Like that doesn't work. But if the numbers are close together, it works very nicely, near doubles. And to be honest, my daughter, who is in 3rd grade now, when we were working on this pretty intensely in 1st grade, she really benefited a lot from near doubles when we were working with flashcards, because we did flashcards with her. I mean, immensely. We'd end up with like 7 plus 6. Well, she'd know what 6 plus 6 was, and then she could do it. So it may not feel to you like the most intuitive approach, but for some children, for my daughter, it actually resonated really, really well, and it helped her get over that bridge of being able to a point where she could memorize them and just know them by rote, right? Because she understood how to get them if she forgot. It was really important. So this is doubles. And the last one I kind of made mention of before. This is a method for making 10, called making 10. So what you're doing is you're trying to find numbers, or numbers, I should say, to start with, that actually add up to be 10. So again, on the last one, the strategy is I know my 1 plus 1s, 2 plus 2s, 3 plus 3, 4 plus 4, 5. I know all my doubles. On this one, what I learned first instead is I learned the actual values that add up to being 10. And for instance, I know that 2 plus 8 is 10, and I know that 3 plus 7 is 10. I know that 6 plus 4 is 10, and I know that 5 plus 5 is 10. And I skipped the 1 plus 9. I don't know why, but I did. Okay, so these are the numbers that I would learn the values for first, and they're all special because they all equal 10. And so instead, what happens is when I encounter something that doesn't equal 10, right? So I get something that's 8 plus 6, and I know, well, that doesn't equal 10. I can start with the 8 or I can start with the 6. This one shows it starting with the 8, and I say, oh, but I know that 8 plus 2 is 10, and 6 is just 4 more than 2. So I look at the 6 and I say, okay, well, I used up 2 of them here. I need 4 more of them here to give me my 4. So again, you don't have to like the strategy, but if you have a child that this works for, wouldn't you like to be able to use a strategy that helps them out? That's the idea. The idea is having a tool belt full of lots of things, so when something doesn't work, you can try something else. Okay, and making 10 is another popular strategy. The other thing is that you will have curriculums, and whether it's these strategies or something else that happens in the next 5 years that you encounter and you're like, well, I didn't do it that way, but they're wanting you to do it that way now, right? Or at the very least, they're wanting you to start with that idea and then broaden their scope of what they're thinking about. So these are 3 basic addition strategies. This is all about single-digit addition, right? These 3 strategies are all about single-digit addition. What we're going to look at next is going to be talking about addition in a more broad sense. Like what happens if it's not single-digit addition, right? What if we're looking at things that have double digits or triple digits? What do we do with those? So the next ones are actually called algorithms. Algorithms mean that they're processes that we work through, right? Like think about a computer algorithm, right? It's the thing that all your social media does to show you whose pictures to look at next, right? It goes through an algorithm. Right, it has this complex algorithm. Well, these are algorithms or different strategies that we're going to use for addition. Okay, so the first one we're going to use is a concrete model. And what this is going to resonate back to is when I showed you the base 10 blocks. Do you remember those? The red ones? This was the big giant one that I couldn't find. Remember that? So you have these little individual pieces called units. You have these longer pieces called longs. We had our flats and so forth. So when I'm working with a concrete model, what I'm really doing with kids is not what I'm going to be showing you. What I'm really doing with kids is I'm getting out the base 10 blocks and they're doing it. Are you with me? Mm-hmm. Okay, and this is like where you start when you're doing this. This is going to establish what we do for addition with the idea of regrouping. You've probably called it carrying, right? Or when you're doing subtraction, we call it regrouping now as well, but you might be more commonly thinking of it as borrowing. And the concrete model establishes what that does and how it works really well. So when I have the number 34, I have 3 longs. So here's 1, 2, and 3. And then I have 4 units. So this is the number 34. And again, what the child is doing is they're in their hands, they have 3 longs and they have 2 units. Okay, like they physically have the objects. And then 18 is 1 long. And now I have 8 units. Okay? And again, the child physically has all these objects. So the first thing that they do is they merge them all together, right? So you take them and you like all dump them together, okay? And you can very clearly see I've got 4 longs, right? But I also have the ability to take some of those little individual units and stick them together like Legos. How many of them will I need to create another long? 10 of them. And if you have manipulatives that actually have the ability to stick together like Legos, this is even easier to see that it now actually is the same length as a long. So for our purposes on our screen, what we're going to do is we're going to recognize that 8 of these and 2 of these is going to turn us into a long. So over here, this is going to equal, well, I already have, whoops, let me do it this way. I already have 4 longs to start with. There's 1, 2, 3, and 4. So there's my 4 longs that I started with, just shifted them to be beside each other. And then the ones that I regrouped into a long create 1 more long. So now I have 5 longs. And how many individual units do I have? 2. And the result is a number that we call 52. Okay? Kinesthetic, right? The kinesthetic learners, the touchy-feely kids, the ones that want to actually see it happen in their hands, you can do this. This works really well with the base 10 blocks. However, if you're teaching money, you can do it with money too, right? Imagine having 3 dimes and 4 pennies, 1 dime and 8 pennies, and talking about the fact that it takes 10 pennies to equal a dime, and I can like collect the 10 pennies and I can exchange them with you. You give me your 10 pennies, I give you a dime, and somehow the child will feel gypped because they just traded in coins. It doesn't work like that, right? They want more coins anyway. It's funny, but anyway, it's worth a different amount, right? And so you can do that. You can also do it with other objects, that would work the same way. You could do this with the idea it has to be base 10 for it to work, or it's going to have those unintended consequences of like my crayon box examples. But anything that has a base 10 structure, you could do this with and talk about regrouping. Okay, let's go to another one. This is the one that you know and at least you feel really familiar with. I don't know about know and love it, but you know it and you feel very familiar with it. This is the standard algorithm. And even if it's the one that you don't start with teaching, it's usually the one kids eventually end up using because it's very efficient. Okay, so efficient means that it's quick. Not necessarily that it's intuitive or makes sense all the time. It doesn't have to, but it means it's quick. Okay, so in the standard algorithm, it's got this unfortunate situation where we do not do it the way we read. We read from left to right, yeah? Mm-hmm. We do not add from left to right. We add from right to left, and we multiply that way and so forth too when we use standard algorithms. That's not super intuitive. Think about that. You just spent, like how many times, how many years at this point having kids learn to read from left to right, and now we're saying go from right to left. So we start on the right-hand side and we say I have 8 plus 4, and that gives me 12. But I don't write the 12 down below. I put a 2 below and I carry the 1, or I regroup the 1. It feels a little bit mysterious. Not only that, but they have to remember which one they regroup and which one they write down below. And believe it or not, writing them in backwards order is not all that uncommon. You will see it happen. Then we go to the next column. We say, okay, I've got the one that I carried, or regrouped, plus the 3, plus the 1 below, and I have a 5. Now think how much better that would be, though, if you paired that with this diagram. And you talked about the fact that the reason that that 1 got regrouped is because we took 10 of the little individual units and we pushed them together and we turned it into a long, and that long moved over into the column with the other longs. That's what's happening. Like totally what is exactly happening. But now it actually has meaning behind it because we didn't start here. We started with the concrete model.
That is good.
Right? It's good stuff. So you're right. Now there's kind of an in-between one of these two. That's our next one. The next one's actually called the expanded algorithm. So it merges a little bit of our standard algorithm with that concrete model. So what we're going to do is instead of writing down 34 and 18, we're going to write down that we have 30 plus 4. And we're going to write down that we have 10 plus 8. So we're expanding it. We've seen expanded algorithm in several places now. This is expanded algorithm written like this. We're actually going to add, and it doesn't matter if we go from left to right or right to left, so that's kind of nice. This is 40, and this is 12. But the 12 is now a 2-digit number that it can also be separated and expanded. So again, efficient it is not. But you can think about what's happening here. Now I have a 40, I have a 10, and I have a 2, which is exactly what happens when I do that regrouping back from the concrete model, right? And now look there. I've got 40 and I've got 10. 4 longs, 1 long. That's 50, and 2 for the 52. Not 54, 52. Sorry. Expanded algorithm. Okay, so you might look at this and say, there is no way under the sun I'm going to teach a kid to do this, and they're going to do this on 50 problems, or whatever number it is. You're right, you're not. Because you know what will happen? After they do this a few times, what will they be able to do? This one. That's the reality. They'll get here. That doesn't mean they have to start here. Okay? All right, let's take a look at the next one. Column addition. Okay, so column addition works a lot like that expanded algorithm did in some senses anyway. I can move from left to right is what I mean by that. So we've got larger numbers just because I want to show you that this makes sense to use in a larger number context. Not all of these algorithms work equally well in every context. So we're going to stack them up just like we have seen the other ones. So I have 1,534, 3,218. And we're actually going to add from left to right. Okay? So in the far left-hand column, what place value am I in? What place value is this left-hand column? I don't have a yeah, what do I call this? I call this the what's place. Thousandths place. This is the thousandths place, right? So over here, this is the one I'm going to be adding first. I'm going to write down sort of a key on the side of this. You wouldn't really be writing this steps down on every problem, but this is 1,000 plus 3,000. That's what we're really doing in that red column. So I'm adding the thousands place, 1,000 plus 3,000. And that's 4,000. Okay, we're not done, but that's the left-hand column. So we move over one. Now I have the 5 and the 2. Well, what I'm really adding is 500 and 200. Again, you wouldn't be really writing down the 500, 200 every time, just for the purposes of this example. We are in 500 and 200 is 700. Okay, next column over. 3 and 4, or 3 and 1. So basically I have 30 and I have 10, which gives me a total of 40. And then my last column, I have a 4 and I have an 8. What is 4 plus 8? 12. Again, it's not efficient. Nobody's claiming it is. It didn't happen quickly. It's not going to be a quick step. But at this point now, I've isolated so that there is either one value or small enough values that I can still deal with it, right? Like this single digit 12 is still not going to exceed, there's not going to be no carrying. There's no regrouping. And I can still add from left to right. So I've got a 4, I've got a 7, and this one I've got a 5 because I have the 4 and the 1, and then I have a 2. So again, am I going to do this forever? Well, absolutely not going to do this forever, but it establishes the ability to move from left to right. Something else to think about, as I'm saying, I'm not going to do this forever. You may have children with special needs that do need to do this longer, or maybe forever, right? There are learning disabilities and needs that require other methods of doing things, and they may actually stick with something longer than your traditional students in your class would. So keeping that in mind too, especially for those of you who plan to work with special education, maybe on a more intense level. Okay, Kinsey says it's her. Okay. All right, here's the next one. This one is interesting, and it has a counterpart when we get to multiplication. This is called the lattice algorithm. So I'm going to do the same thing. I'm going to write the numbers out on top of each other. So 1894 and 3218. And what I'm going to do is underneath them, I'm going to draw like a box. And the box is going to be split into 4 rows because I have 4-digit numbers. So whatever number of digits you have is where you split it. So if you had a 3-digit number, you'd do 3 boxes below, so forth. And then we're going to split our boxes diagonally. I promise we'll get to why in a second. But it looks like a lattice. This is why it's called the lattice algorithm. It's got that image to it. And again, I have the ability to move from left to right, and that's very nice. So I have 1 plus 3. What is 1 plus 3? 4. So if I have a single digit number, the number gets written in the bottom left-hand corner. Here's my 4.
Oh, we were talking about this in one of our classes.
Were they?
Last
Awesome.
semester, and I had no clue what was going on.
Yes. This is the lattice algorithm. All right, my next column, my hundreds column. I have an 8 and a 2. That adds to 10. I have a 2-digit number, so I separate the 2 digits. The 1 goes on the top left, the 0 on the bottom right. Okay. The next one, 9 and 1 is 10 again, 1 top left, 0 bottom right. 8 and 4, 12, 1 top left, 2 bottom right. Okay, so what that does is kind of like with this one over here, it isolates so that I'm doing individual addition facts, right? I'm never adding like 3 or 4 things together. I'm never adding 2-digit things together. It's single-digit addition. And if a child has memorized or is still working on the memorization of individual addition facts, that process is simpler. So what do we do next? Well, the next thing we do is we extend the diagonals down. We're just going to draw them down here further, okay? At this point, I do have to start on the bottom right. I can't start anywhere else. And I add along the diagonal. So this first diagonal, as I add, there's only one number in it, it's a 2. The next diagonal has a 1 and a 0, so it adds to 1. Next one has another 1 and a 0, adding to 1. And the last one has a 1 and a 4, adding to 5. While it does not entirely eliminate the need for regrouping, we didn't regroup anything here, it does minimize the need for regrouping. There are fewer times where you have to regroup. If we had added this number, the original one's given, and used a standard algorithm, we would have had to regroup several times. Here, we didn't end up having to regroup at all. Okay, and our answer there is at the bottom. It's 5,112. Okay, we have more, but I don't feel like I can do justice to opposite change if I talk to you about it in 1 minute. So we're going to pause right there and we'll pick up there on Friday. All right?